everyone. We're delighted to host Glenn Starkman, who just gave the ITC colloquium on one of the puzzling facts that is not fully understood about the universe. I guess there are many more, but they are usually on smaller scales. Right. And we'll hear more from Glenn in a few minutes. We'll start with Ana-Roxana, who is a graduate student in our astronomy department, and she will describe stellar shells in the Illustris simulation, which look very much like shells we see on the sky, as we'll hear. Then we'll hear from Rosalba Perna, who is giving the CFA colloquium today. She also used to be a student here from the physics department many years ago. How many was it? 20?
It's not that.
But actually, when we met yesterday with Rosalba, I thought that she looks just the same. She looks so young. She is young, yes. And Rosalba is doing a lot of interesting work, and she's currently at the Stony Brook University with connections to the Simons Center for Computational Astrophysics. And she will talk about, at the lunch, about the interactions between multiple supermassive black holes and galactic nuclei, a solution to the final Parsec problem. Then we'll hear from Glenn, who will talk about macroscopic dark matter. And finally, we'll hear from Pranab Ghosh, that is visiting us from UT Austin. And he will talk about, where is Pranab? Over there.
Here I am.
And he will tell us about Super-Chandra masses of supernova type 1a progenitors. Ana-Roxana.
Hello everyone. Today I'll talk to you about shell galaxies in the Illustris simulation. This is work I've done with my advisor here, Professor Lars Lundqvist, where we studied shell galaxies in a cosmological context. And here on the left, I'm showing an example of a few famous shell galaxies. And by shells, we mean very low surface brightness tidal debris that appear as interleaved caustics on both sides of the galaxy center, and they have large opening angles. And one might be tempted to believe that such images correspond to very rare galaxies, but in fact, about a fifth of the galaxies, of the massive elliptical galaxies in our universe, exhibit such shells. Shells have also gained a bit more attention last year because the neutron star merger actually happened in a shell galaxy, and I'm showing the host galaxy on the right side here. Oftentimes you'll hear astronomers classifying tidal features into very distinct classes, ranging from what I refer to as shells in my work, which is highlighted in the left here, and then ranging as we increase the angular momentum of the satellite's orbit, or in other words, as we go to a more circular orbit, to what I like to call wrappings and eventually streams. And I like to show this plot because it's important, especially when we compare to observations, to know that the properties of the satellites that form these different features will vary significantly depending on which type of features we include in our sample and how we define shells. Furthermore, shells have been defined oftentimes as belonging to several subclasses. For instance, type 1 shells are shells where the shells are aligned with the major axis of the galaxy, and type 2 shells correspond to more randomly distributed shells. There's also a third type, which corresponds to even more random distribution of shells. So most of my work has involved working with the Illustris simulation, which is a cosmological hydrodynamical simulation. Here I'm showing in the upper left corner an observed shell galaxy, NGC 3923, and I'm comparing to images of 5 shell galaxies that we find in Illustris. And you can see not only that the galaxies look very similar, but we also sample a wide variety of shell morphologies in our simulation. We used the 220 most massive galaxies in Illustris, and this corresponds to a mass cut of 6 × 10⁻12 solar masses in M200 crit. And we used a 2-step identification process. In the first step, we choose to wear the observer's hat. We do something similar to what observers do. And we'd look at stellar mass surface density images of these galaxies, looking at 3 different projections as well as 2 different photometries. And also similar to observers, we implement a scoring system in order to find all the galaxies that are candidates for having shells. In the second step, I wear a hat that I'm more accustomed to, and we actually look at the simulation and try and trace back all the stars that belong to these galaxies in order to identify the stars that form the shells. This is somewhat similar to building a merger tree catalog, but we call them stellar history catalogs, and the main difference is that we study the properties of stars in far more detail. We are interested in three main times in the history of these stars, that is formation, accretion, and stripping time. And for all of this time, we save different properties of the stars as well as the progenitors that they were gravitationally bound to. In this way, we build post-processing tools. We are able to identify all the satellites ever accreted by a galaxy. And we look in turn at all of the satellites, both in configuration space, which is shown here as the first three columns, as well as phase space, which is radial velocity versus radial distance. And the nice thing about shells is that they're very easy to recognize in phase space. And this is because they appear as caustics, which peak at around a radial velocity of 0. These points correspond to the apocenters of the orbits of these stars. Moreover, the way to think about it is that as the stars from a satellite start to be stripped, because the stars will have a range of energies and orbital periods, those stars that have shorter orbital periods will start to overlap stars with longer orbital periods, and this will cause the wraps that we see in the bottom right corner. So, looking at all the galaxies that we identify in this way to have shells, out of the 220, 18% have shells, and this fraction increases if we look at more massive galaxies. So more massive galaxies are more likely to have shells. Moreover, galaxies at redshift 0 are more likely to have shells compared to galaxies at higher redshifts. But we are also interested in knowing what type of progenitors can form these shells. And this study was the first cosmological study of the self-consistent formation of shells. Previous studies have oftentimes appealed to isolated mergers where the satellites were initialized on perfectly radial orbits. So you'd often find in the literature that these shells formed through radial minor mergers. However, these studies did not include the effects of dynamical friction or the self-consistent evolution of the host galaxy. And there have also been several observations over the past years that say that these shells might actually have a major merger origin. So what we did then was to collect all the progenitors that managed to form shells and to study their properties. And here I'm showing the distribution of all the satellites ever accreted by those shell galaxies in blue, and those satellites that managed to form shells are shown in red. And you can see that we actually find that massive satellites are more likely to form these shell systems. In fact, the stellar mass ratio of these shell-forming progenitors range between 1 to 10 to 1 to 1, and the total mass ratio ranges between 1 to 100 to 1 to 1. We looked at a range of other properties for these satellites, and we identified the ones that we believe are key in determining whether you can form a shell. And the three that we found to be most important is that the satellite must arrive on a radial orbit, it must be relatively massive compared to the host, and it must be accreted between 4 and 8 gigayears ago. If you are going to be accreted too early, many of those shells would have phase mixed. If you were accreted way too soon compared to redshift 0, then most likely you haven't had enough time to strip the stars and form the shells. An interesting effect of the fact that many of these systems form through relatively major merger is that they leave a unique imprint in the metallicity of the stars. So here I'm looking at a shell galaxy, and what we find is that oftentimes the shells on the outskirts can be more red or more metal-rich compared to stars at similar radii in the host galaxy. And this is a prediction that we made in a paper that was published last summer, and it was very nicely confirmed for observations with the Hyper Supreme Cam led by Erin Kadofong and Jenny Green at Princeton. One thing I want to emphasize, though, is that when we say that the shells are more metal-rich, we are comparing to stars at similar galactocentric radii in the host galaxy. So here in box 2 is centered on a shell versus box 5, which is at the same galactocentric radii, but it has lower metallicity. It is not, in almost all cases, the very center core of the host galaxy will still be more metal-rich than the shells. We have two other predictions in that paper, which we hope will also be confirmed by observations in the near future. One of them is that we should observe a gradient in the metallicity of the shells, because we start stripping stars from the outskirts of the satellite, where the metallicity is lower. The effect of that is that the outermost shell will be more metal poor, and as we move towards the center, the inner shells, which probe the core stars from the satellite, will be more metal rich. The second one is that about a quarter of the shell systems that we find in Illustris actually have multiple shell-forming progenitors. And oftentimes, these shells will have different metallicity signatures. So with sufficiently high-precision metallicity measurements, we might be able to identify systems that have more than one progenitor and to tell which shell came from which satellite. In this way, we might even be able to constrain the mass merger ratio for these systems. I'll conclude by telling you a bit about work that I'm currently doing doing at the moment, which is to look at a distribution of the stellar halo and dark matter halo, and the shape of these halos, in particular for shell galaxies. So here I'm considering the best fit ellipsoid, with the free axes being A, B, and C, starting with A being the largest axis and going to the smallest axis, C. And in the plot I'm showing on the left, you can see prolate galaxies marked by the red area and oblate ones in the bottom right corner. And we mark on this plot by orange those satellites that, those galaxies that have shells, in red, a particular type of shell, the type 1 shells, where the shells are aligned with the major axis of the galaxy. And in blue is a mass-matched sample of galaxies that don't have shells. And we see straight away that the dots in orange are preferentially located in the prolate region. 72% of shell galaxies have a prolate stellar halo, and 9 out of 10 type 1 shell galaxies are prolate. So especially type 1 shells are very likely to be in a stellar halo. There is one such galaxy that you can find in the oblate region, and we took a better look at this type 1 shell to figure out why it is not prolate. And we find a very interesting effect where in red here, I'm showing the in situ stellar component, and with the shape being measured between 0.5 and 25 effective radii. And you can see that the in situ component is oblate for this galaxy. However, in magenta, I'm showing the total stellar component. And you can see that the halo shape transitions from being oblate at small radii to being prolate at large radii. And we find that this is due to the ex situ component, the stars that have been stripped from other satellites, and in particular, stars that have been stripped from the shell-forming progenitor. Those are shown in light blue, and you can see that they lie in the prolate region. Here I'm showing in the bottom left corner an actual image of this shell galaxy. Moreover, we can also look at the dark matter halo. And what we find is that in the inner regions, this dark matter halo is preferentially spherical. But especially after the merger, this dark matter halo will transition to being prolate at similar large radii. And we traced back this in redshift, and we found that this transition happens around the time of the merger with the shell-forming progenitor. So we found that these mergers not only influence what the metallicity of the stars will be at large radii, but also the difference in halo shapes that you might see. So to conclude, we used Illustris to look at 220 massive galaxies at redshift 0. 18% of those have shells, and we find that these shells formed mostly through massive mergers between 1 to 10 to 1 to 1 in stellar mass ratio. They were equated on radial orbits between 4 and 8 gigayears ago. They have very interesting metallicity signatures, and most of them are found in prolate halos. Thank you. There could definitely be shells in the Milky Way, and it would be very exciting to find those. Yes. It is possible to form such shells, and also to detect them.
What is the criterion for separating shells from streams?
So in our case, it's visual. So in the first step, we look at the entire stellar mass surface density of the galaxy. And in the second step, because we can identify the exact progenitor of those shells, we can see that we can distinguish more easily between a shell and a stream.
There's some number where you say that the surface density is above below.
It is not a cut in surface density. It is morphological, the distinction.
When you monitor and see increasing metallicity as number of mergers, do you see any particular trend? Quantitative trend?
By that, you mean, in particular, looking at...
When you go from one merger to two mergers to three mergers?
So in this particular case, I'm showing the satellites that belong to only one merger in the bottom. So we have especially looked at the mergers that produce the shells. And in those cases, the mergers will leave a significant imprint in the distribution of the metals.
I have a population question for you. So I guess you said 20% of the galaxies have shells observed. So I was wondering how does that compare to the spectrum you see, and whether that changes at all as a function of your surface brightness
Right. So we do see 18% of the systems that we analyze to have shells, but when we compare to observations, of course, it depends a lot on surface brightness limit increasing. That will lead you to detect more shells. Also aperture size, because many of these shells are at very large distances, 100 kpc or more around the host galaxy. So all of these will, and projection effects, because we have the advantage of looking at all three projections. So 18% is an upper limit on the number of shells. Observations usually detect far less than that.
One follow-up on that, or not Pranab said briefly. I'm guessing that most of the shells come from the increasingly very flat system.
A very,
I don't know if that's true or not, but it does raise the question, are there any shell-like structures within the dark matter?
yeah, so.
And would they have any consequences, say, for gravitational lensing?
So that is, okay, first things first, we did look at other properties of the satellites, and we found that we don't see a strong correlation with whether a satellite will form shells or not based on other properties. But that being said, we do expect to see some shells in the dark matter. They will oftentimes have less contrast, and I do not know whether this would have any effect on gravitational lensing. Yeah, that would be very interesting to look into. Thank you.
All right, so continuing on the topic of galaxies, I'll be talking about a recent paper which has been led by my graduate student TIFR, who defended his thesis last week. And I should say that in addition to acknowledging here the work has been done all by him, but also the slides I actually borrowed from his PhD thesis, so they're so nice and with animations, which I would know how to make. As I was thinking about a paper to discuss, a work to discuss, completely unrelated to the topic of the colloquium today, so there was another reason for why I picked this paper. Anybody can note a fun fact about the authors? Avi?
Except for Jerry Ostraker. There are students of Avi wrote.
So I thought it would be especially appropriate on the, I didn't pay notice until actually I was putting together. So, okay. All right, so let's discuss the problem. So as you all know, supermassive black holes are ubiquitous in the center of in galactic centers, and this is our well-known Sagittarius star. It's been a long subject of investigation, how these black holes were assembled. So both from theory and observations, actually, let me bring here all the point. So both theory and observations point to the same type of a scenario in which a supermassive black hole assembly follows the process of galaxy formation through merger and accretion. So smaller galaxies at higher redshifts get together and merge, and the central black holes will eventually merge, but that's the point of the discussion. And then further accretion of gas will contribute to the further growth. So let's see what is the problem here. So before that, actually, let me be sure, like this is just from observation. So the fact that there is a point before the merger where there is more than a black hole in the center has already been seen in some observation via detection of multiple supermassive black hole systems, and this is one example. So both theory and observation point to the fact that this supermassive black hole came from mergers of smaller systems. So let's see what is their journey from two supermassive black holes to one merged one. So it starts when they're far away, as the galaxies are starting to merge, they're isolated, and then as they get closer, a binary is formed. And this is stage one. And then there is stage two, which is the one I will be discussing a little bit more in a moment, which is the process during which the binary hardens get closer to one another until to a point when it's close enough, the gravitational wave radiations take over, and then the merger can occur very efficiently. So let's see what are the issues here. And there is a very interesting plot from a paper from early many years ago. So as you see, this has probably been discussed in the literature for quite some time now. So early on, and initially, when the black holes are still further away, the dominant mechanism for the black holes to come closer to one another is dynamical friction. So interaction with stars and gas will basically create a drag, and the black hole slows down and loses energy, angular momentum, and comes closer and closer to the center. Now, as you see here, so what happens as the black holes come together, as somebody's phone. As black holes, so the two black holes are coming together, and then you keep the merging process. As this stars, the binary interacts with stars, what happens is that stars can get captured by the black hole. And this results in the very well-known process of lost cone depletion. So you need stars in order to create dynamical friction, in order for the binary to get harder, and therefore being able to eventually merge, where on the other hand, you're capturing stars, and therefore you are depleting the region that you need in order to be efficient with the process. So this was very well emphasized in this early paper, where you see there are two lines here, one which indicates what the time scale would be for merger if the lost cone was entirely depleted. So if there are, imagine that every star that approach gets captured or disrupted, then this is full lost cone, like empty lost cone. Then basically what you see, that the merger time becomes larger than the Hubble time. So basically what is telling you that there is no merger, or merger is very inefficient. On the other hand, if I do have a pointer that comes very handy, if it works. Okay, no, it doesn't matter. On the other hand, if the lost cone is now depleted, thank you very much. Okay, perfect. Okay, so then the merger can occur on a time scale which is shorter than the Hubble time, which is what you want. And this is the gravitational wave time scale, which becomes very short once this region is reached. So this is basically what I just discussed. So there are these two limiting situations that were discussed here: the empty lost cone, so no stars around, and the full lost cone of many stars around. And this is so the region here, which is where, depending on what happens to the stars, constitutes the bottleneck. And this is a well-known problem in astrophysics called the final passer problem, that you all have heard about. So the question is how to bypass this. So if the lost cone is depleted, then this, we would infer basically the mergers will not occur. We would have many more systems with multiple black holes. So this is the background. So what we particularly investigated in this paper is the effect of multi-body interaction. So let's say that as you keep on merging galaxies, and therefore the black holes in the center. So what happens if a binary is still there before a third black hole from a new merger makes to the core? So then multi-body black hole interaction will be inevitable. And this is something that will accelerate the black hole coalescences. And these are only some of the papers that I've pointed out, including Avis and the student at the Decade Code, pointing out this phenomenon. So this is this is actually an observational slide just to show that evidence for system of more than 2 black holes, more than 2 sources, let's say in the center, have been already exist also from an observational point of view. So this is a scenario that we investigated theoretically, and this slide kind of summarizes the whole idea. So what we did was following the galaxy merger trees from very early universe used in the Millennium simulation. And then as galaxies are merged, then we incorporated that with an N-body code, which my graduate student developed actually from scratch for this and other projects. And this is just details of what it does. The code so includes all these things. So at early times when the black holes are further away from one another, then dynamical friction dominates. But then as they get closer and closer and new black holes come in, then also three-body interactions start to become important. And these are the ones that we are mostly interested in here. So in terms of how to investigate this with the code that we had. So we decided to focus on the 2 extreme scenario. One, which is the loss cone. First of all, let's discuss this one first. So neglectional loss cone, meaning that the assumption is that dynamical friction operates all the way to the end. So this is where you do expect, indeed, mergers occurring without problems. But and then the other extreme case, which is the new and the more interesting one, which is what happens if the loss cone on the other end is entirely depleted, and therefore all that can help is three-body interaction. So I should say that in the literature, so there's been a lot of discussion this last Parsec problem, and a lot of the studies have mostly gone into finding ways to replete the loss cone. So given that that's the origin of the problem, a lot of work is being going to discuss a lot of very different phenomena that can they can alleviate this issue of loss cone depletion and with the replenishing it. On the other hand, we was like, okay, let's make the most extreme assumption that there is nothing works and therefore it's depleted. Can we? Can we still merge? And basically, then obviously the true evolution you expect it to be something in between. And then this is just so a slide that I picked one of the many papers that figure from one of the many papers that summarizes the point. And basically, what we found is that the average lifetime. So this is the 2 extreme model. One, the full loss cone, which again is not surprising that we find that they do merge. But what's interesting is in the empty loss cone case, where the bottom line is that we found that three-body interaction alone are sufficient to harden the binaries and therefore basically make it emerge on a time scale which is shorter than the Hubble time, and therefore that can constitute a solution to the last Parsec problem. Then I had a few slides on the gravitational wave background that comes as a part of it's a side, but I guess I can or not to describe it. When you have all these supermassive black holes merging, they will also contribute to the gravitational wave background. This is something that's for the future very much of interest for PTAs and current surveys that are future and current. They're being planned, and especially the square kilometer wave. Bottom line is that different models will predict different. And I'm killing also this laser. Predict a different amplitude for the background, and therefore we computed the same also with our model. And basically, just the bottom line here is that right now, the limits with current surveys are not. They don't have enough sensitivity to be able to discriminate about among different scenarios. But with the square kilometer array, with the data that are being planned, it will go deep enough. So this is what it will achieve. Will basically be able to use this gravitational wave background observations as a test of different models, and therefore, what actually constitutes a solution to the last Parsec problem, and that's it. divided. It was 3 hours 51. It was a slow one, but anyway. I'm already qualified for next year, so I qualified on this one, but New York City was faster. So anyway, it's
So I'm trying to understand how this actually solves what Parsec problem is. With 3, 2 of them merge, and then I'm left with 2 again.
So the third helps the main binary to merge, and then you start having more than you have. So it's a continuous process. So the problem, once you have the 2 main one, let's say the first 2 that were left, then the third one was left, and then you have grown the bigger one, and then you have the one, and then you can imagine another one coming in. So you're sort of, having a third that helps the 2 there behind.
Does this mean that if you look at the centers of most galaxies, if you need this mechanism to solve the fast Parsec problem, you should usually see a binary, you should see 2 black holes?
Yeah, so in some cases they are seen, but it's not easy to see supermassive black holes in. And this is like observers who probably know a lot more than me, but it is being seen, which is why I was showing some of the slides. So
Even just the binary.
yeah.
Potential.
Yeah, that's right. So the triaxiality is one of the things that was discussed as a way to alleviate the lost cone problem. That's right.
Yes, Dan and then Rosalba.
Great. Do you expect the 3-body interaction to excite any eccentricity in the binary?
Right. Yes. So we also had a huge discussion on eccentricity. Yes. So there will be more eccentric, in fact, and I didn't put any of that. And in fact, also will affect the gravitational wave background, which will have a band. Yeah. So we calculate, and it just for this talk, it's not.
I guess also just quickly related, do you think that the third black hole will also help to refill the lost cone since it brings on its own?
It's also that's right. So it will also help in that direction.
Just a quick question. When you're following these merger trees,
Right.
How frequently does this happen? In other words, is this something we should expect in all of the galaxies, or does it apply to only a fraction of the cases where you might have the double black holes?
Right, so in this merger tree simulation, so the millennium is following the galaxies, and the assumption would be that there is a black hole in each one. So, yeah, so that's basically...
What I guess I'm saying is that you have a merger, so in what fraction of the time do you have a third merger, a fourth merger, and so forth?
Right. So it depends. So we have actually a number of figures in the paper that show for different mass ratios. Yes. Right. So it's a fraction. So depending on redshift and all, can be between 0.2, 0.3 to 0.6, 0.7. I'm going by memory of it. But yeah, it.
Thank you for a wonderful talk.
Let's thank Rosalba.
Oops. Just a sec. Yeah. Great, so I'd like to tell you about macroscopic dark matter and start by reminding you that for most of the last 40 or 50 years, the leading candidate for dark matter has been particles from beyond the standard model, motivated by a miracle that happens in theories in which there are particles that are more massive than protons and neutrons that have weak-like interactions, which is that we end up with about the right amount of dark matter. But of course, we haven't seen beyond the standard model of physics yet at the LHC, and we haven't detected this dark matter, which brings us to maybe start thinking more and more carefully about all the other possibilities there are for what dark matter could be. Now, of course, we've also been looking for other things like axions, and people have been thinking about anything from charged dark matter to wimpzillas to things with all sorts of strange names. But when we say dark, what do we really know about that word dark? We automatically think, I think, after 40 years of thinking about WIMPs, that it means that their cross-sections with ordinary matter is small. But really that's not true, because what really matters are interaction rates. And interaction rates depend on the products of number densities and cross-sections. And there's two ways to get interaction rates small. One is to make the cross-section small, and the other one is to make the number density small. So what really matters is the cross-section divided by the mass, not the cross-section. So dark matter can be low mass and very low cross-section, or high mass and not so low cross-section. So I want to explore the possibility of that second one, which is that dark matter is even macroscopic, that it's things that are more like a gram. So way back, I think starting in the 90s, and there's this nice paper by Mac in 2007, people explored things that were more like up to the Planck mass, but I want to explore the idea that things are much heavier than that, their masses are measured in grams, and so here are black holes along this purple line, here are things that are rocks along this black line, and this green line would be things that were like of nuclear density. Okay. So what could they be? Well, you might imagine stellar remnants and planets and other things like that, except we know that dark matter had to be assembled before Big Bang nucleosynthesis, and we don't have stars before Big Bang nucleosynthesis, and we certainly don't have planets. But still, within the standard model, we could imagine assembling things like strange quark nuggets or strange baryonic matter or strange chiral liquid drops, and these things go by all sorts of names, and we may or may not know the standard model physics of their assembly, and we don't even know the standard model physics yet, whether such things are actually stable within the standard model. We don't know how to calculate whether they are or aren't, but we don't know how to calculate whether they are or aren't. Okay? And of course, we could have primordial black holes, and that's a fascinating idea that has come to get a lot more attention later. I'm going to focus mostly on this, but some of what I said will apply to that. Of course, there's lots of ways to get objects like this beyond the standard model. You could imagine adding axions, and that the axion bubbles would help hold together these things. Or you can imagine things that go on in supersymmetry, or things that have topological defects. But I'm going to try not to care, although I must admit that part of what excites me is the idea that dark matter may be a standard model phenomena after all, which would be incredibly disappointing, but also incredibly exciting for a model that has had so many successes. So what do we know about this macroscopic dark matter, these macros? So I'm going to try to focus on just the properties that depend on the masses of the objects and their cross-sections. So there's all sorts of limits or ways to probe them that will depend on if they have charges or if they destabilize ordinary matter, but let's try to ignore that, because those are going to be very model-specific. We're going to have gravitational effects, and then we're just going to have the fact that big lumps of stuff have a really hard time avoiding scattering off of baryons and off of each other and off of photons. And so you end up discovering, first of all, that up here, for things that are, whose masses are best described in terms of solar masses, somewhere up here, or Earth masses, that they cause microlensing events. And we've known that for a long time, although, of course, most of these microlensing, the problem with most of the limits on microlensing, so this is in the mass versus cross-section plane, these limits are relatively shallow. What I mean by that is, although it's true that a one solar mass objects can't be all of the dark matter, they could be 10% of the dark matter, and you evade those microlensing limits. Okay? And unlike particles, where you expect all particles of a given type to have exactly the same mass, If you're making composite objects, they're going to have some initial mass function. And we have no idea what that initial mass function is, so we can imagine it being very widely spread out from solar masses down to something much smaller or much bigger. Recently, there has been new microlensing data from CWRU, which extends those limits down further to more like 10 to the 20 grams, and also probably to more stringent limits, so that it appears quite difficult to have very much dark matter of this sort that's between about 10 to the 20 and 26. And then femtolensing that comes from observation of gamma ray spectra, gamma ray burst events rather. So it seems to be a preference in terms of what's left for objects that are between about 50 grams and 10 to the 17th grams, but that's an awfully wide range. Below 50 grams, we start to get things like, it turns out that the best limit over much of that range is mica, so rock that was buried under the earth for hundreds of millions of years, and you take a square meter of it and you look at it, you etch it, you look very carefully for tracks in that rock, you don't find any, and you discover that if the dark matter would have passed through it, which it would have had a hard time not doing, that it has to be heavier than about 55 grams. Again, these limits depend on, are written in such a way that it's only if it's 100% of the dark matter. And then there are for long time limits coming from seismology, in particular of the moon. The Apollo astronauts left some seismometers on the moon, and NASA kindly operated them for a few years, and then shut them off. But those limits are actually a fair bit weaker, I think, than were previously quoted, and in particular don't, at best, extend down to this green line where things would have nuclear density. And that's because it's really hard to make little things like this hit something and make things with kilometer-long wavelength seismic waves. Okay. So you see that there's a whole big range of masses and cross-sections in which we do not yet know whether there's dark matter there. Up here, we start to impact cosmology by changing the CMB. And although I'm putting this limit there, one can imagine interesting physics kind of sitting at the edge there. Okay. So there's a lot of physics to explore. As I said, there's also some model-dependent constraints that you could imagine. Like, we would like the sun to keep existing. Not only would we like it to keep existing, it does exist. And so if the macros, if these macros are more stable forms of ordinary matter up to very large masses than more stable forms of standard model matter than ordinary matter is, then they better not get captured in the sun. So you have to watch out. And that would really, so in models like that, you really have essentially no space for dark matter. So if this ordinary dark matter would turn the sun into something else, it probably doesn't exist, although I think I shouldn't have extended this as far as the black hole line where they wouldn't get captured. Okay. So there's lots of other considerations, like you better make sure they're stable, but what I want to talk about is the things that we can imagine doing in the future to look and probe that big window that's still open. Okay. And one of those things actually depends on a detector that's already there, the Auger detector, because as these objects come through the atmosphere, they cause nitrogen fluorescence. And you might say, well, Auger didn't see that nitrogen fluorescence, therefore they didn't come through the atmosphere. But it turns out that if they did cause that fluorescence and Auger detected it, it would have thrown it away. Because these things, instead of moving at nearly the speed of light, are moving at 10 to the minus 3 at the speed of light, and Auger doesn't want to look at things moving 10 to the minus 3 at the speed of light, so they have hardware and software triggers to prevent that. And so what we're looking at, and we're talking to some of the folks on Auger, is changing that. And so with ultra-high energy cosmic ray detectors like Auger and GEMUSO, you can make a big dent in what you can see. I think an exciting thing that we've just realized that we're about to put out a paper in the next couple of days is these will also cause distortions in the CMB. And that's because they are reservoirs of heat. So if you have an object that's macroscopic and it's formed at a temperature of 10 to the 12, 10 to the 15 degrees, when the universe is very early in the history of the universe, they cool much more slowly than does the background plasma. They stay warmer than the background plasma, and so they cool. Their interiors cool very slowly. Their exteriors also cool slowly, and they stay quite a bit warmer than the CMB. It turns out they produce mu and y distortions, and the exciting thing is that those mu and y distortions look like they could even be detected by the types of satellites that people are proposing building, like Pixie. So, dark matter doesn't have to interact weakly if it's very massive. It could even be within the standard model. There are unconstrained regions of size and mass. There are all sorts of probes that you can imagine looking at. I didn't mention all of them. For example, gravitational waves. Such strongly interacting dark matter candidates may or may not be relevant to outstanding issues like the final Parsec problem. But we certainly need to keep looking, and there's a lot more thinking to do on how to look for them. Thanks. And I want to extend an invitation to two conferences at CASE, one June 1st to 4th on 58 years of the standard model, and one June 4th to 8th on things beyond the standard model. So think about this. If someone gave you a choice, I'll either fire a cannon at you, right, with a cannonball, or I'll fire something with the exact same momentum, but it's a micron across. Which would you choose? The micron. So the answer is no. It doesn't. It probably wouldn't even hurt.
So we should monitor asteroids with roughly the same mass, but you're saying these objects, an asteroid has a cross section
Right.
which is much bigger than a centimeter.
Exactly. It's much worse to get hit by an asteroid than one of these. In fact, perhaps one of the best things you could do is if we could get everyone to go, well, you put new windows in here. But if we got people to go to all the old windows, right, and look at them very carefully, we could probably do a pretty good search that would extend quite a ways into this parameter space because they would leave tracks in the windows.
I have some in my home.
I'll be over later.
Oh, the plates. Josh, what about the plates?
That's true. We have 500,000 pieces of glass right across the
And they've probably been sitting there for 100 years?
Well, the oldest ones, yes.
There we go.
And it's digitized, so we could.
Right. So
How big the tracks are.
glass.
We'll look for the tracks.
Well, yeah. So we should talk about that because it depends on the material. So glass plate windows, old especially in old skyscrapers are good. But the other thing that's good is so people who go and look for oil, they bring back shale samples, and so that mica band was from about a square meter. There's a lot more than a square meter of shale samples out there. And there's a distinctive signature that the geologists tell us would be left of where you could actually probably see the melt on either end. And so if we could just get petroleum exploration companies, they keep these. They don't throw them away. We could just go look at them, and we might be able to look for this. We might be able to put interesting limits. Yeah.
I'm just wondering, when you're computing tracks, what is the physics that you're putting in? So these are small objects that have mass. Is it just that?
The only thing we put in, because we try to put the minimal thing in, is that as they go through, they scatter every proton and neutron along the way, right? And they give them velocities that are comparable to their velocities. It's elastic scattering, and so that basically you effectively instantaneously, it's hypersonic, Mach hundreds, going through and melting a cylinder through the object. Yeah.
So if the dark matter candidates are charged, you would principally be protected from them on Earth by the Earth magnetosphere and the solar wind and things. So if you don't see the tracks, does that really eliminate particles entirely of that mass?
If you don't see the tracks.
So on the low end.
Yeah. 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 So I don't think these things would have much charge. the charge to mass ratio would be incredibly small, I think. It's very hard to have a very big charge to mass ratio when you're so massive. So.
I was wondering if you managed to adapt the Piaget experiment to detect the slower moving tracks. How much would it be dominated by the contamination, or what's your event rate?
Well, let's see. Yeah, so you can see that we're pretty sure that we could cover this whole region all the way up to about, from this is about 55. This is like 100 grams, 55 grams. We could get all the way up to almost 10 to the 5 grams. It's a very distinctive signature. The things that they were trying to avoid seeing were things like lightning, which doesn't look much like this, and because these are slower moving than lightning. That's one nice thing, and the other thing is they're very straight, right? These things, whereas lightning is not particularly straight and it tends to branch off and stuff like that. So we're told that if we can change the trigger, this is probably not hard to see.
Would these appear in any way like shooting stars? I mean, shooting stars are very small particles that come through the atmosphere. They're not moving at relatively speed. If you set up a camera in a very dark location, would that set any useful?
Yeah, so we looked at that. It appears that amateur meteor searches, there are searches for meteors. These look just like meteors, except kind of 10 times faster. So they'd be a little bit distinctive. They tend to, down here where we're looking, they tend to not be as bright as meteors, so you can't see them anywhere as far away. And so the fact that Auger is, so sensitive really helps. So the answers appeared to be that meteor searches were not as good as ultra-high energy cosmic ray detectors. But yeah, it's clearly an interesting idea. There's lots of things like that, like, what about the hydrophones that they use to listen for things like submarines, for example? And there's all sorts of things like that. So there's also some things where you can imagine. One of I think the hardest thing is, you have this piece of rock a meter squared that's been sitting under the ground for about 300 million years. So you need 300 million meter squared years of exposure in order to beat that mica. That's not easy.
How do you, it clicks on.
Okay, so supernovae are gigantic stellar explosions that can sometimes outshine the whole galaxy, this fellow here. And, oh yeah, I was going to show you their little movie about their appearance and disappearance. This is just to set the stage. I'll take a couple of minutes. Yeah. Okay, so. Oh, it's not working for some reason. Yeah. So, suddenly appears a very bright star and fade away. So late October it appeared. This is a supernova of type 1a in this galaxy, 1365, found by robotic search, which was looking for something, robotic work which was looking for something else. Suddenly late October, this fellow brightened up and disappeared by late January, early February. Yeah, same thing shown 3 times. Fine. All right. And again, setting the stage, taking 2 minutes. Spectral classification, so depending on whether they have hydrogen or they don't, they are called type 1 and type 2. And type 1 then is further subdivided depending on whether I have silicon or no silicon, and if they have no silicon, helium or no helium. These lines show you. These are the famous silicon lines. Our interest today is in type 1a supernovae, and they are supposed to be, again, one cartoon. The idea here is that it's thermonuclear burst in an accreting white dwarf in a binary. So this is the white dwarf accreting from the companion star, and eventually carbon at the center ignites, and that's how it works. The other types are all core collapse supernovae, which we are not concerned with today. And of course, the idea there is that you forget all these details. These are numerical simulations. If you ignite carbon at the center, it goes through what's called deflagration. The ignition proceeds, the wave proceeds at subsonic speed first, then goes into a detonation, which is supersonic, and that combination is supposed to forget all the details. That's not our purpose today. What we are interested in starts from the idea that, which is famous now because of use in cosmology, that type 1a supernovae are standard candles, i.e. they have basically the same intrinsic luminosity or total power output that is, it sort of makes the light curve up and down universal and roughly universal, but it can be made very precisely universal by that stretching method, and that led to the discovery of accelerating universe and so on. But even that's not the purpose. The idea is, what's that constant amount of energy output related to? And that's, of course, the famous Chandrasekhar limit, which is one of the basic cornerstones of physics, that you can't really support a mass more than the Chandra mass by degenerate electron pressure. And that's what leads to, supports the basic idea of universal peak luminosity, which was at the heart of all that. This is what we are really after. The Super-Chandra supernova 1A progenitors, they were found. You know, all this was a beautiful story. A wrench was thrown in the works in 2006 by a famous paper by Howell et al. They found this supernova whose progenitor then could be inferred to have a mass of about 2 solar masses. This is from the nickel ejecta, which are measured. That's how it was jokingly called the champagne supernova by David Branch, who wrote the News and Views article in Nature. David Branch, the great expert from University of Oklahoma on the supernovae. And then since that friend, several others have been found. About 10 are known now. I would think 5 are pretty sure measurements of mass, and the others are more uncertain. The mass range that's found is about 2.0 to 2.8, 2 to 3 solar masses, let's say. Now, how do you do that? And that's our concern today, so I'll take maybe 5 minutes to tell you what we have done on that. A very popular idea is that differential rotation inside the white dwarf can sustain such masses. That if the fact that if you have uniform rotation, you can't sustain anything more than a few percent more than the Chandra mass has been known since the mid-60s. In the late 60s, Oestreicher and co-authors, Oestreicher, Bodenheimer, and so on, showed that if you have differential rotation, you can go up to 3 or 4 solar masses. Classic work. But that depends, of course, on the internal rotation profile. I'll do it this way. Internal rotation profile of the white dwarf, and in an accreting binary like this, that needs to be understood, what the rotation profile is. So to tell you the story, that there is that binary, the companion is transferring angular momentum, forms a disk, deposits angular momentum on the surface of the white dwarf sitting there, and then the whatever viscosity you have transports. This is viscosity inside the white dwarf matter. That then transports angular momentum from the surface to the center, and the internal rotation profile depends on the transport properties of angular momentum. That's what concerns us. So, 2 minutes more. Viscosity, take a quick look at the possible viscosities in that kind of degenerate matter. One is, of course, high viscosity, which produces fast transport of angular momentum. Hydrodynamic viscosity. 2 major kinds are known. Kelvin-Helmholtz instability, which is done by shear instability, different layers going at different velocities. And baroclinic instability, which is more subtle but very important, very large, can be very large. This is when you have certain situations where surfaces of constant pressure and density no longer coincide as they want. If you have differentially rotating systems in hydrostatic equilibrium, then you can have that instability. That also transports angular momentum very fast. And all of this is described in terms of something called Richardson number. That's the Brunt-Weisseller frequency by shear squared. Brunt-Weisseller is your buoyancy frequency. If you have something stabilized, stratified in a stabilized way, and if you push a bit of mass, it jiggles, and that's the frequency, buoyancy frequency. That stabilizes, and this shear destabilizes. So Richardson number is a measure of their balance, and above a certain critical value, Kelvin-Hills instability shuts off. That's also understandable. Then shear, this effect is much larger than this. On the other hand, you can have low viscosity and slow transport. Look at the bottom of the slide. And that's usually associated with Zahn's name. And this is possible even when you don't have this. Because of thermal diffusion, you can still destabilize and produce slow transport. So with all this now, I'll tell you what kind of rotation regimes one can infer inside white dwarfs, which are accreting angular momentum on the surface from the companion star and transporting it through the white dwarf. One case, which is uniform rotation, is obtained when you have Kelvin-Helmholtz plus baroclinic instability. This can be worked out. This was known before us. Saiwan Nomoto showed this. We also showed this. That's myself and Craig Wheeler at the University of Texas. The profile looks, oh my God. Yeah. The profile looks like this. What you have is angular velocity versus time, angular velocity versus the radius of the star, time being the third coordinate there. And so uniform value keeps on increasing, and this is a stacking of those individual cases in 2 dimensions. So that's the uniform rotation. This is the differential rotation, which you can also have with the same viscosity as Kelvin-Helmholtz or baroclinic. And if you think, how is that possible, we'll come to that in about half a minute. We showed that. That wasn't known before. And before you think there is any voodoo here, we'll show you that it's all consistent with laws of physics. So that's what it looks like. Same coding. The angular velocity profile changing with time, and it going up like this. Okay. Finally, Zahn, the low secular viscosity, will also give you a differential rotation with a peak here, and that's also well known before us. And finally, just to complete the zoo, Yoon and Langer gave a model some time ago where they had a situation where the viscosity was dominated by Kelvin-Helmholtz here, but the critical Richardson number was reached here, so it shut up, and the low Zahn viscosity took over here, and that gives you a rotation profile like that. So the idea is that, well, maybe I should clarify first. How is it that baroclinic instability plus Kelvin-Helmholtz instability can give 2 regimes? I'm putting on the same viscosity, I'm getting 2 kinds of rotation profiles. How is that possible? And there is no great mystery there. The uniform rotation happens at high Richardson number. That's, of course, almost tautology. That Richardson number goes as shear to the -2. So if it's high Richardson number, then it's very low shear, almost uniform rotation, and the other end is low Richardson number. It's possible because of this. This is the culprit, the baroclinic instability. It scales with the Richardson number in 2 different ways, in 2 different regimes. There is a critical value, this fellow, and so if you're below that, it scales with this, and above that scales like that. And so the viscous stress scales as sigma squared, shear squared in that regime, and that's the reason. You'll notice that both are nonlinear, but differently nonlinear. And so that, summing up, those are the various regimes. All right. So this is a plot of the whole zoo in terms of viscosity here on log scale and Richardson number on log scale. These blue puffs are the regions of differential rotation. This red puff is the nearly solid body, nearly uniform rotation. There's a transition region which is very poorly understood. All right. And so finally, the critical mass would need to be calculated, and that happens when at some critical value of the mass, above Chandra mass, when carbon ignition occurs. And the calculation of that is going on. We need to understand the effect of rotation profile on that mass, and if there are questions, we'll discuss them. So that's it. The conclusions are for you to see that, yes, differential rotation can happen. depends on the details of the angular momentum transport and the viscosity. And so we have to see what nature does. And dual regimes are possible, apparently paradoxical, but not really. And Super-Chandra masses, of course, that mass which we need to calculate, putting on various building blocks, depends on the angular momentum profile. Thank you. Excellent point. Yeah, had these beasts appeared before that? Yeah. So your question, when rephrased, might be, how is it that they don't throw a spanner in the whole works? No, they appear clearly as outliers. They have spectral anomalies. You don't see them in garden variety, your quote-unquote normal, what David Branch calls normal supernova 1A. And these are well recorded. We know about 10. When the first 3-4 came out, people said, are we throwing all of this stuff out of the window, this wonderful cosmological work? No, but those are the, the normal cases, the garden variety. There's, in fact, the distribution of progenitor masses, if you think of that. We don't have time to do that's ongoing work. There is a broad peak around Chandra mass. Then there are sub-Chandra, and then there are somewhat Super-Chandra, but it cuts off around 1.7, 1.8 solar masses. These are way out there. Well said. Oh my God. Detailed knowledge will kill you. Yeah.
I was just going to say there is very likely a reason why most of them, peak around the Chandrasekhar mass, which is that when you do the binary evolution models, one of the problems with making enough type 1A supernovae through the single degenerate channel is that you run out of mass. And so it's kind of hard to find the ones that are going to be even Chandrasekhar mass, much less super Chandrasekhar. So I don't know if nature was kind in eliminating differentiation or kind in having a limited mass budget, perhaps.
Yeah, that's what we have been trying to answer. And you have been particularly clear in your pointing out in your papers that the supply of mass from the companion runs out at one point. So that determines, among other criteria, what the mass of this white dwarf would be before it explodes. Right. Yes, you have made that point very clear.
Even a little bit, you can still have a significant spin down time.
Yeah, that's the other thing. We didn't have time to say. I'll say 2 words about your spin up, spin down mechanism. She's one of the pioneers of that. There were several groups pointing this out. The idea is that when you were merrily spinning up this white dwarf with all your angular momentum accretion, and you were making Super-Chandra progenitors, how would you make them explode? What happens is that while all this rotation and differential rotation makes you able to build up the mass of the white dwarf, it also reduces the density at the center because of centrifugal forces. So that even when the accretion stops, let's say, as Roseanne was saying, the supply has run out, it won't explode because its central density is too low. You have to get rid of that angular momentum somehow. This is the spin-up, spin-down mechanism. Unless you get rid of it, it can't explode.
We ran to our time limit. Other questions can be asked.
Yes.
Let's thank all of
tough part is to we have to have a good for a while. And so here, the building will start. First of all, how much mass there is running out of mass. Number two,
I'm planning.
T by W.